Welcome back. As the second and final part of our exponents unit, we're going to look at what's called scientific notation. And the idea behind scientific notation is that a lot of times in science, you have very, very large numbers or very, very small numbers, and you don't want to write a bunch of zeros to express that. So first, let's go way back to maybe even elementary school, and let's think about, let's say the number 1, 2, 3, 4. Well, we make a lot of assumptions whenever we write numbers, but what does this actually mean? Well, note that this is 1,000 plus 200 plus 30 plus 4, right? And again, this is obvious, but we're going to use things that are obvious to build examples and build up kind of our intuition here. Well, this is 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4 times 1. Note 1, 2, 3, 4, 1, 2, 3, 4, right? So using what we learned about exponents, 1,000 is 10 times 10 times 10, so we get 1 times 10 cubed plus 2 times 10 squared plus 3 times 10 to the 1 plus 4 times 10 to the 0. Remember, 10 to the 0 is 1. So notice 3, 2, 1, 0. That's what it means to have 1, 2, 3, 4. Is we have 1 in the 10 to the 3 place, we have 2 in the 10 to the 2 place, we have 3 in 10 to the 1 place, and we have 4 in 10 to the 0 place. Right, and if you have decimals, let's say 0.1, let's use different numbers. Let's use 4, 6. Well, that is 4 times 1/10 plus 6 times 1 all over 100, which is going to be 4 times 10 to the negative 1 plus 6 times 10 to the negative 2. So our whole idea of place value systems in the base, what we call base 10, is that we write our numbers by exponents of 10. So we have 10, the 10 cubed place, the 10 squared place, and maybe I should draw blanks here. Let me just redo all of this. Whenever we write a number, right, there are infinite number of zeros going off to the left, right, because 0, 0, 0, 0, 0, 0, blah, 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 7 is just 7, right? So we can write an infinite number of zeros going off to the left. Likewise, we can write an infinite number of zeros going past the decimal, right, because 7.4 is the same thing as 7.4, 0, 0, 0, 0, 0, forever. So we have a 10 to 0 place, which is our 1's place. We have 10 to the 1, which is our 10's place. 10 to the 2, which is our 100th place. And then on the other side of the, right, and this keeps going off to the left. On the right side of the decimal, we just keep going down. We have 2, 1, 0. What comes after that? Well, negative 1, or the tenths place, the 1/10ths place. And we have the 1/100ths place, and the 1/1000ths place. Right, and we keep on going off to the right. So that's what it means for it to be base 10. Remember we talked about last time, if we can go all the way back there. We did a lot last time. Base, right? Base 10. And that's where we're at with this, is the base for our number system is 10. You can have base 2, you can have base 8, you can have other bases, but here and in general we use base 10. Okay, so what is scientific notation? We've done a lot of talking about numbers. Scientific notation looks like a times 10 to the power of n, and we have restrictions, and these restrictions are very important. A has to be a number. It could be any decimal number between 1, and it could be equal to 1, and 10, but it cannot be equal to 10. And n has to be an integer, which means a whole number. It could be a negative whole number, but it has to be a whole number. So let's look at some examples. Is 1.85 times 10 to the negative 2 in scientific notation? Well, let's look. Is this between 1 and 10? Yes. Is this an integer? Yes. So this is in scientific notation. Let's look at some close relatives. 1.85 times 10 maybe to the negative 2/3. Is that in scientific notation? Well, we have a number between 1 and 10, so that works. But this number up here is not an integer. So no. What about 0.85 times 10 to the negative 2? Well, this is an integer. That's fine. But this is not a number between 1 and 10. So that's not. Then what about, let's say, 10 times 10 to the negative 2? Is that? Well, again, this is an integer, but this is not less than 10. That's equal to 10. So no. Okay, now let's write some stuff in scientific notation. Or let's take something in scientific notation and convert it to decimal. 3.7 times 10 to the 4. This is between 0 and 1. This is an integer. I'm sorry, this is between 1 and 10, and this is an integer. So what does this mean? This means 3.7 times 10 times 10 times 10 times 10, which is 3.7 times 1, 0, 0, 0, 0, 10,000. Okay, every time we multiply by 10, we move the decimal place over 1. So we get 37 times, we multiplied by 10, so we pop off 1 0. Multiply by 10 again, pop off another 0. Multiply by 10 again, pop off another 0. Multiply by 10 again, pop off another 0. Notice that's just times 1, so that doesn't do anything because 1's the identity. So there's our answer. We could put a comma there if we want. Okay. Next example. Let's write 0.000007301 in scientific notation. So the question we have is, how many times do we have to multiply by 10 to get this number between 1 and 10? So that's equivalent. Whenever we multiply by 10, we're basically moving the decimal point to the right one. So we have to multiply 1 time, 2 times, 3 times, 4 times, 5 times, 6 times. Now 7.301 is between 1 and 10. So we went 1, 2, 3, 4, 5, 6. 6 times. So we take 7.301 times 10, and since this is a decimal, it's going to be to the power of negative that number we counted. Since this is not that it's a decimal, but that there's nothing to the left of the decimal point. If everything's on the right of the decimal point, this is going to be negative. So let's check it. 7.301. And remember, infinite number of zeros off to the left. times 10 to the negative 6, times 10 to the negative 5, times 10 to the negative 4, negative 3, negative 2, negative 1. 10 to the 0 is 1, so we stop. So that's that number. Do we have the same number of zeros? We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Good. Same number. Okay, you can see that, especially once we get larger and larger and larger and larger, that what I have circled here is way more compact than what our initial problem had. It looks a lot nicer too. Okay, let's do 3.7 times 10 to the negative 4 in decimal. Well, 3.7. This is times 10 to the negative 4, times 10 to the negative 3, negative 2, negative 1, 0. Stop. Fill in your zeros. There's your answer. And maybe I'll rewrite it just to, whoops. Let's take off the outline. That is 0.00037. Okay. So now let's do some multiplication. In general, a times 10 to the power of m times b times 10 to the power of n. Well, we can use the associativity property. So that's the same thing as a times 10 to the m times b times 10 to the n. Okay, we can use the commutativity property and say that's the same thing as a times b times 10 to the m times 10 to the n. Associativity property, we have a times b times 10 to the power of m plus n, right? That's what we learned from exponents last time. Okay, the only problem is if, and I'll put a blue dotted border around this, because a times b could be bigger than 10, right? Remember, for scientific notation, we have to be somewhere. We could include 1, go up to 10, but we cannot include 10. So a times b could be bigger than 10. It could be, it can't be less than 1, but it could be bigger than 10. So we may have to reduce it, right? And the way we would do that, notice a times b will never be bigger than 100, right? Because a, the biggest it can be, is like 9.999, we'll call it 10, but it can't actually be 10, right? So it has to be strictly less than 10. And the b, the biggest it can be, is 10. So it's going to be less than 100. So it may be, our number here is going to be anywhere, a times b is going to be anywhere from 1 to 100, not including 100. So if it's between 1 and 10, we're done. More likely, it's going to be between 10 and 100, in which case we need to take AB, divide it by 10, and notice that'll get us down between 1 and 10, and multiply that by 10, right? So what we've done here, we haven't changed anything, right? We divided by 10 and multiplied by 10, same number. And so then we can simplify this. Okay, so it's going to be, whenever you multiply, it'll be one of these two forms. All right, that's kind of abstract. Let's look at an example. Say 3 times 10 to the 8 times 6.8 times 10 to the negative 13. Okay, remember, from what we got before, we can go ahead and simplify this down to 3 times 6 times 10 to the 8 minus 13. I don't know why I put parentheses on those, but maybe I won't. 3.6, or not 3.6, 3 times 6 times, okay, 3 times 6 is 18. 10 to the power of 8 minus 13 is minus 5. Now, this is an integer, that's fine. The problem is that this is too big. So we're going to have to divide by 10, which is 1.8 times, if we divide by 10, we have to multiply by 10, right? So this is, maybe I'll do it in blue. This is the same thing as this, right? No difference. Times 10 to the minus 5. Now we can group these two things together. Maybe I shouldn't circle it, but I'll group those two things together. That's 1.8 times 10 to the 1 minus 5, which is 1.8 times 10 to the minus 4. Well, it would help if I actually used the right numbers, I suppose. I apologize about that. Let's call this just 6 instead of 6.8. Sorry, I forgot to include the 0.8 in there. So if it was just 3 times 10 to the 6 times 6 times 10 to the negative 13, my bad. Okay, let's do a more convoluted one. 8.2, and this is going to require some pretty extensive multiplication on my part, times 10 to the 6, times 1.5 times 10 to the negative 3, times 1.9 times 10 to the negative 7. And you're about to see how bad I am at multiplication. So we'll work through this together. So we can, kind of generalizing the two-dimensional case, or the two-number case, we can go ahead and write this as 8.2 times 1.5 times 1.9 times 10 to the 6 times 10 to the negative 3 times 10 to the negative 7. Okay, let's crank out some multiplication. Here's how I'm going to do it. 8.2 times, maybe I'll write it over here. We're going to take a break and do some multiplication. 8.2 times 1.5. Well, that's the same thing as 8.2 times 1 plus a half, which is just 8.2 plus 4.1, which is 12.3. Okay, so then we need to do 12.3 times 1.9, and I'll do this 12.3 times 1.9. 9 times 3 is 27, carry the 2. 9 times 2 is 18, 19, 20. Carry the 2. 9 times 1 is 9, plus 2 is 11. Okay, bring down our 0. Then 3, 2, 1, we get 7. I don't know how I just did that. Ignore that line there. 7, 3, 3, 2. And we have 2 numbers behind the decimal place, so we have 2 numbers behind the decimal place there. So our final number here is going to be, okay, we're done with multiplication. That's the same thing as 23.37 times 10 to the 6 minus 3 minus 7. Okay, this is 23.37 times 10, 10, yep. 6 minus 3 is going to be 3. 3 minus 7 is minus 4. This number is too big, so divide by 10, and then multiply this one by 10. That's 2.337 times 10 times 10 to the minus 4. Again, notice, I can't stress this enough, this number and these are the same thing. We haven't changed anything. So then we get 2.337 times 10 to the 1 minus 4, which is minus 3. Okay, we've got 2 more examples to get through. Time to do some division. 9, let's do it in general first. A times 10 to the m divided by b times 10 to the n. Let's kind of prove this out. This is the same thing as a times 10 to the m times 1 all over b times 10 to the n. Okay, well that's the same thing as 1 all over b times 10 to the, maybe I'll split that out into two steps, 1 all over 10 to the n. Okay, using the associativity property. I'm sorry, one more thing here. Do a times 10n, it's 1 all over b times 10 to the negative n, right? So using the associativity property, we can drop the parentheses. And then using the commutativity property, we can put a times 1 over b together. And we can reintroduce the associativity property. We can put 10 to the m times 10 to the negative n together. So we get a over b. I don't know why I put parentheses there. I don't need them. A over b times 10 to the m minus n. Okay, we're going to have the inverse problem here, as what we had with multiplication. If a is between 1 and 10, then the smallest a can be is 1. If b is between 1 and 10, the largest it can be is 10, but it can't be 10. So our a over b is going to be strictly less than that. Sorry, greater than that. So it could be, and kind of the other way around, a could be 10, but not 10. So we have this. It's fine if it's between 1 and 10. We're good. But if it is between 1/10 and 1, we're not good anymore. So what we need to do, what we possibly could do, so I'm going to kind of box this like this. We could need to multiply by 10. And if we do that, then we would have 10 times a over b times, if we multiply by 10, we have to divide by 10, right? 1 over 10 times 10 to the m minus n, which is 10 a over b times 10 to the m minus n minus 1. So it could be we need to take off a 10, or rescale, basically. It could be one of those two cases. Okay, now we'll do an example. We'll do 3 times, I don't know why I'm putting parentheses whenever I don't need them, 3 times 10 to the 3, all over 9 times 10 to the negative 2. Okay, so what we have here is, using what we just determined over here, we can take a and b and divide those. 3 over 9 times 10 to the 3 times 10 to the minus, it's going to, times 1 all over 10 to the minus 2. 3 over 9 is 1/3. And then that's going to be 10 to the 3 times 10 to the 2, right? Because minus 2 is just 2, which is 1/3. And I'm going to put that as 0.33 repeating, times 10 to the 5. Notice this number is too small, so we're going to multiply by 10, and then divide by 10. Ta-da! So we get this number. One more example. This is going to be more of like an applied science one. The speed of light, which is denoted as c, is approximately 3 times 10 to the power of 8 meters per second. the sun is 1.5 times 10 to 11 meters away. How long does it take for sunlight to reach Earth? It's a good question. So, first we're going to do some dimensional analysis. We have meters per second, and we have meters. How can we combine these to give us seconds? Well, if we take meters per second and we multiply by 1 all over meters, we get 1 all over seconds. So then if we take both sides, raise it to the power of -1, we get seconds. So we need to take C, which is in meters per second, multiply it by 1.5 times 10 to the 11 meters. We need to sorry, I'm being stupid. I mean, that works. What I did works. How can we combine these two things together? Let's go back to that question. Well, if we actually invert this one, we get seconds per meter times meters, which is seconds. So we just need to invert. So if we have C, we need to invert it. And we'll call this distance D. Times D is going to be what we want. So C is 3 times 10 to the 8 meters per second. Inverse times D, which is 1.5 times 10 to the 11 meters. Oh, don't forget your meters. Up here we get, we didn't really talk about this, but whenever you do an inverse, if you remember a property that we had before, let's go ahead and write it out. It distributes over multiplication. In seconds, we're now in seconds per meter, times 1.5 times 10 to the 11 meters. Okay, we know how to multiply these two things together. We get 3 inverse is 1/3, so we get 1.5 divided by 3 times 10 to the -8 times 10 to the 11. 1.5 divided by 3 is 1/2. Sorry, we're doing decimals. 0.5 times 10 to the -8 plus 11 is 3. We need to rescale this, and that gives us 5 times 10 squared. So, when did I drop my seconds? This is seconds, seconds, seconds. So 5 times 10 squared seconds. Well, we solved the problem, but let's think about this a little further. 5 times 10 square seconds is 5 times 100 seconds, which is 500 seconds. How many minutes is that? Well, 500 seconds divided by 60 seconds per minute is going to be 500 divided by 60. Seconds divided by seconds per minute. Well, seconds divided by seconds per minute is going to be seconds times minute per second. The seconds cancel out, you get minutes. Maybe I need to write min instead of m. That way we're not confusing it with meters. So we get 5 over 600 minutes. I'm sorry, 500 over 60 minutes. Doing some quick division. Let's see, we can go in there, 9 times 6, 8 times 6 is 48. We get 20, so that's 1/3. So it takes about 8 1/3 minutes. Okay, that's going to be everything for scientific notation. Again, this is something that you should practice to get more familiar and comfortable with.